For that we need the basic general equations. Also we might need. Next is important to be aware of that. And then I have the s by dt, the ds by dp at t is dp by dt at b. Then I have dt by dp at x is dp. Then the last relation is minus ds by dt at t is dv by. These are the maximum relations. Make sure I present them correctly. And then we also have the objective is to express all these coefficients. It might not be possible always. The objective is to express in terms of a pressure explicit equation of state and its derivatives with respect to volume and temperature. Because that's what would be directly given to us. Whereas Cv expresses a function of V and V or. So that is the energetic data. P is a mechanical data. So these coefficients, some of the coefficients we will see are directly expressed in terms of the equation of state alone. They can be determined by the equation of state alone. So then starting from E, suppose we show that E by dV, and as far as definition is concerned, we define Cv, the specific heat constant volume, as the derivative of the internal energy with respect to temperature. So now E by dV, we show yesterday that this is. And for the other relation, we proceed from the fundamental equation. We also get that E by dT at T Cv is T ds by. We get an alternate expression for Cv. Right? So that is some textbooks use this to define Cv. We shortly look at the motivation for that. Motivation comes from again classical thermodynamics. Why should we define anything in this manner? Right? And then I have E of dP. E by dP at T would be, for that I would first regard, since I got E of dP, I would regard E of dP as arising from E of dt, because D can be expressed in terms of T and T. That way I get to solve, because dP by dt is less than 0. Basically it's not equal to 0. So that is B can be inverted in principle. Expressed in terms of P and P, and further the inverse function theorem would give that dV by dt at T is 1 over dP by dt, and T is minus dP by dt. Right? this, so it will imply that dE by dt is easily written as dE by dt. I already know what dE by dt is, so that is dE by divided by dE by, because dE by dt is the inverse of dV by dV. Now dE by dt, we will take a closer look at it, but first we just write the expression. So that will involve two terms from the chain. One would be dE by dt. So nothing to much, it's not being transformed, so we get the term as it is. Plus dE by now CB dE by dV, I can again write divided by, okay, there's nothing in this, but this will now give negative of dV by dt by dV by somewhat complicated form, but we will see that it can be simplified once we define Cp. So I may now write this as Cp minus P this whole thing will turn out to be Cp and plus P and this will turn out to be Cp. You can ask why should this be Cp? We will prove that shortly, right? And so if you look at this, you have to understand that when you define Cp, it is either dE by dt at constant volume. But Cp is not equal to dE by dt at constant pressure. You can easily see that that will happen only when dP by dt is 0. Right? So if dP by dt is greater than 0, which is typically the case, what can you say about dE by dt at P? Is it going to be greater than Cp or less than Cp? Looking at this is, assume this is Cp for now, right? And then tell me, based on what you know, it will be less than Cp, because if dP by dt greater than Cp, you see, so one where it sits where dP by dt will actually be less than 0, and in that case, of course, dE by dt would happen. But if dP by dt greater than 0, this is typically the case for the ideal gas equation of state is R over P, which is always greater than 0, right? So if then dE by dt at P is clearly less than Cp, right? Because dP by dV is less than Cp, always. dP by dt, right? It can be also less than 0. It can even be equal to 0. We see that, but typically, generically, dP by dt is normally greater than 0, constant volume. But there is no restriction on that. Now we move to the next one. We are looking at X, right? It's simply ds by dt is given by Maxwell's relation, directly related to the equation of state, right? So, and then ds by dt at P is from there is equal to Cv by P. Now we come to ds by dP. Now ds by dP again can be, right, although it is in a somewhat roundabout way, but it can be easily inferred from the Maxwell's relation minus dP by dt at P. We want to explain how we come to the S by dt. And again, you can do it in many ways. So I'm going to write this like this. So if you look at the motivation for why I want to look at, I've already got what I want here is ds by dt at t. So, right? So I need s to be expressed as a function of t and p. So I have already derivated of s with respect to p and p. So the natural, logical conclusion would be to look at s as a function of p and t as arriving from s as a function of p and t. Right? Then p expressed as a function of p and t. So we already know that those derivatives of what they mean. Right? That is what it is. Now look at this again by the chain rule. I get one term from here, that will be ds by dt p, that's the original representation, s in the p and t, plus ds by dv at constant temperature, and dv by dt at p. So this now is cv. ds by dt is dv by dt v times minus dv by dt. I'm sorry, this is cv by t. Right? ds by dt is cv by t. So we have now this is equal to minus dp by dt. So now I can multiply through by the temperature, right? So what I get is ds by dt at t is cv minus d. So the question is, why should I now define cv to be given by this? There are many ways in which I can define cv, but since it has occurred at this stage, I now define cp. So you might want to know why we should define cv. Why is that quantity cp? For that, the only motivation I can give is the classical thermodynamics, where we had, for instance, this is how cv was introduced in the classical thermodynamics. The first book. So we had a model for Q. This entropy was not the original quantity, maybe heat and work. And from that, the internal energy and entropy came as consequences. Right? So we have to go back to the original. Now, if I want to define Cp, obviously it would be like this. When I have to consider this as the latent heat at constant pressure, then the corresponding coefficient multiplying the temperature derivative would be Cp. This is how Cp is defined in classical thermodynamics. In fact, you can show that since we know that what is the relation between Cp and Cv, since we know that, for instance, we can assume this to be per unit mole, so that I get this to be all per mole. Specific heats also become per mole. You can define the rate of heating for unit mole of gas, for instance, fluid. So from to establish the connection between these is not an independent quantity. They would be independent. There is no relation between P and V, but we know that, we assume rather that the pressure is related to volume and temperature by an equation of state, and such an equation of state exists for all substance. So if I use that, then clearly P dot is dP by dV times P dot plus dP by dT times P dot. So if I substitute that here, I get a relationship between lambda V and lambda P and CV and CP, and you will easily verify that the CP is actually related to CP by this relation. This relation is already there. We then go into great details. Right? So we can see. So one way of calling this as CP would be to say that all the equations based on equilibrium are consistent with the relations of classical thermodynamics of reversible processes. Since we obtain Cp to be equal to this, I can now define Cp to be this. On the contrary, if you want to focus on the entropy, we already showed that ds by dt is qr by t. This is the basic property of the second law of thermodynamics. So now this can be written as ds by, if I want to write it in terms of P, if I want to choose P as the variable, P and temperature, right? So this can be written as ds by dt at fixed temperature times dP by dt, which is all in terms of time, but we want to get only at the coefficients, plus ds by dt at P times dt by dV. Equal to qr by t. So obviously, if I'm expressing this in terms of pressure, I want to write this as lambda P dP by dt plus Cp dt by dt. So from that, I can easily infer that the Cp, this is the qr by t, so this has to be by t. By comparing the coefficient of dT by dt, that is the time, the temperature by the time, right? I can easily see that Cp is Tds by dt. So that gives another expression for Cp in terms of the entropy. Of course, if I were to express this in terms of V and T, I would get Cv expressed like this. But I have chosen, that is a good motivation, because both Cp and Cv are defined in the same way. Cp is T ds by dt at constant volume, and Cp is T ds by dt at constant pressure, which is why most of the books probably choose that. Easy to remember. However, I have done it differently because this is the internal energy was discovered first, and so Cv automatically becomes it's an earlier expression. Cv defined as dE by dt receives the definition of Cv or the expression of Cv through the entropy. So I have chosen to define it like this and get this as a consequence. This comes out as a result. But it's up to you, whichever way you want to define it. But the basic definition of Cv and Cv are coming from the model for Q. This is the most basic. It receives the discovery of internal energy as well as entropy. But since now our basic quantities include the internal energy, entropy, and so on, various other quantities, we obviously want to define these quantities in terms of them rather than through the heat model, right? So, are there any questions on this, on the motivation for defining Cp? So, I have now defined this, so clearly you can now be convinced that this is actually Cp. So many possible arguments are given for you to convince yourself that that quantity is Cp. Because you can define anything you want as Cp. So any group of quantities, but it should have some consistency and some meaning. Right? So that is what it is. Now we take the other quantity, enthalpy. Right? So H again. consider in terms of B and T. Now H is naturally a function of S and T. Now let you do that as to do a simpler method. H is a function of S and P, and I can express S and P as functions of B and T. So I want H as a function of B and T. Right? So I can always go back to the fundamental equation. I already know the derivative of S with respect to B and T, and also T with respect to B and T. So obviously I can apply the chain rule. This is a very direct application of the chain rule. Function of two variables which are in turn defined as functions of two other variables. But however, I am going to use a shorter method because H we know is E plus BB. Right? So if I want the derivative of H with respect to B and T, then I have to express everything in terms of B and T. So I can write this as H of BE is E of BE plus B of BE times D. So now what is dH by dV? Equal to dH by dV. Can you write what is dH by dV? Just differentiate that with respect to volume, term by term. Come to the board and yeah, please. So everything is a function of volume and temperature. I'm going to differentiate with respect to volume, keeping temperature fixed. So differentiate term by term. That's all. There's nothing to it. Don't think it's complicated. dV, everything is derivative. Okay, plus. Now it's a product. So we have to get two terms. dV by dV times not B. Okay, fine. Yeah. Fine. Plus. What is the second term? V times derivative of V with respect to itself is 1, because V and T are the independent variables. So when you are differentiating V, there is no question of constant and variable. Yeah, so that's it. So that is what it is. So now I know that this is ddV by dt at constant volume minus T. Right? Plus d dV by dV plus E. Also the D gets cancelled and we get this to be d dV by dt. That's all. There's nothing much to look at this any further. But however, what is interesting to be dH by dV at constant volume. Now I get two terms. Sorry, again I get two terms. So this will be dE by dV at constant volume. That is the specific heat at constant volume. dE by dV. Plus, now I will differentiate. So this will be dV by dt at D. And then plus what? 0. Right? So the differentiating V with respect to temperature, keeping the volume fixed. The derivative of some quantity keeping itself fixed is obviously 0. Right? So the V is also the independent variable. So the derivative of that with respect to T has to be 0. Right? Keeping V fixed. That is what you have to keep in mind. Right? So that is what it is. So this is CV plus V times dP by dt at P. So what can you say about the magnitude of dH by dt in relation to Cv? Is it going to be greater than Cv or? If dP by dt is greater than 0, which is typically the case, clearly this would be greater than Cv if dP by is greater than 0. You see the relationship between these derivatives. Now we will go to H versus P and T. That is probably the last of the important relations, because the others we won't be able to. For G, for A we haven't really looked at anyway. See, so dH by what I will do is write it here. So H is now expressed as a function of P and T. So I can again use the same. But now I regard this as expressed as a function of, but one option is that I can, since I've got H as a function of P and T, I can regard H of PT. So there are so many different ways of doing it. And apply the chain, right? Another is simply, since I know E as a function, since I have already done that method, I can simply regard that E where P remains as it is, and P obviously is also to be expressed as a function of P and T. So I can now differentiate term by term, right? So dH by dP dE by dP at T. Whereas what? So dE by dP plus then dV by dP at fixed temperature. Differentiate with respect to pressure plus V times 1. So I already have dE by dP, so that is, we can look at that a bit more carefully. So we get a simpler expression. So dE by dP is P, dP by dP minus P divided by dP by dP. So some of it is sequential. The point is that if I had probably gone to this, for instance, probably everything is going to be probably an easier method would have been to do this. Anyway, there are so many methods. You can try some of the other methods and check if you're getting the same relations, right? So I have this plus P again P over dP by dP at T plus P. So this is going to cancel with this. So we get this to be T dP by dP. So some of these are, of course, this is more compactly related to the dV by dt. We just see that dV by dt divided by dV by dV is simply the negative of dV by dt at P. Yes.
So this dV by dt at constant V. So you said if it is greater than 0, then Cv is greater than 0. So for a polytropic oscillator, we have to have the dV by dt is less than 0.
No, we are not talking about a particular process. We are talking about the property of the equation of state. That's a different question you are asking. We are not talking about in particular processes what will happen. Right? This is about the equation of state. Can the equation of state can substances exist for which dP by dt at fixed volume is greater than 0? To give you the answer, there is a case. One is a well-known case of water, which we will look at later shortly. Because we want to also see what is the use of deriving all that. It might just look like a maze of expressions. We have to make some sense out of it, right? You see that water at 4 degrees centigrade is a classic case where dP by dt actually vanishes. So to the temperatures lower than 4 degrees, actually that's an anomalous behavior. dP by dt will actually be less than C. That is one instance where Cp would actually be less than Cv. I am not aware of any other instance. So this is basically a material property and it doesn't directly relate to particular processes undergone by it. Right? We have to make that distinction. So this is what it is. So I can also write this as P minus P. So now we will look at dE by dH by dE at P is equal to really dE by dE at P plus, so I am going to differentiate here. Pressure is kept fixed, so this P I don't have to differentiate, plus P dE by dE at P, which is dE by dE at P, plus or rather minus P dE by dE at P by dE by dE at P. So now if you see dE by dt we know is Cp plus this, right? dE by dt. So this is Cp plus P dP by dt. That is what I have already derived. And then I have minus of the same quantity. So I am making use of the relations I already have. So we have established that this group of quantities is Cp. So I have dE by dt is Cp plus this, and dH by dt is Cp plus that. Of course, that is dE by dt at P minus P dP by dt by dP by dt. So that will get cancelled, and then I get Cp is equal to. So some books also use this as the definition of Cp. So that way, there is some consistency with Cv is defined as dE by dt at P, and Cp is defined as dH by dt at P. That's another way of looking at it. So some books there is some similarity between the two. Cv is E is a natural function for Cp, you can argue, and derivative with respect to T at fixed volume gives Cv. You can say that H correspondingly, right, turns out to be a natural quantity for Cp, and its derivative with respect to T at fixed pressure may be defined, may be taken to define Cp, but we don't adopt that. The enthalpy is something that came later, and certainly we would I'm quite happy with the way we have introduced. Cv is defined as dE by dt, and Cp could be defined as ds by dt at P. Of course, Cv is also equal to ds by dt at constant volume. Important relation is Cp is given by dH by dt at P. This now comes as a consequence of the earlier definitions and derivations. Okay. So the other quantities that are A, of course, A directly is given in terms of T and P. Directly it is given. Right? So, but however, what we wanted to express everything in terms of pressure explicit equation of state quantities and Cv, that is not going to be quite possible because we don't know how to further reduce this entropy, so further knowledge of that. Right? So we have to leave it as it is. dA by dt is minus S. The same way would be G. Right? But however, I can ask what is A as a function of P and T. That is not obvious. Right? So maybe we can do that. And now we can see, before we go to that, we can now identify what these relations become for ideal gases. Since I have all of them on the board, and if you look at the first thing you recognize is that the ideal gases P is equal to RT by V, and clearly this is equal to 0. So whatever put in the brackets are correspond to ideal gas. You can easily verify T dP by dt minus P is 0 for the ideal gas. So that means we recover the result that dE by dt is 0 for the ideal gas. That means internal energy of the ideal gas is a function of temperature only. This is actually a major consequence of the first law of thermodynamics. But here we recover that same result. So that is what I have. And what can you say about dE by dt should also then vanish, right? Because V is a function of T and V, and then I say dE by dV is 0 for ideal gas. That means E is a function of T alone. So dE by dV must also vanish. That's clearly also to vanish. So this is also equal to 0 for the ideal gas. Right? So now important relation is this Cp, which I could define like this, and it gives rise to this. You can easily show that Cp minus Cv of the ideal gas is equal to R. So we are now listing some of the well-known properties of the ideal gas. Ideal gas, the immediate thing that comes to mind is the equation of state, P equal to RT by V. But you should also be aware of other important properties that follow, either we can regard as consequence of the first law of thermodynamics, which is integrated into all these fundamental equations, the first and second laws, right? So what I am saying is that you can recover all those important properties. The internal energy of the ideal gas is a function of temperature. Further, Cp minus Cv is equal to R. If you substitute for dP by dt and dP by dV, you will get that. I'll let you simply verify that. Now, what can you say about the enthalpy? Since H is E plus PV, right? For the ideal gas, PV of the ideal gas is simply RT. So clearly that automatically means, just from the definition of the enthalpy, you can conclude the enthalpy of the ideal gas is also a function of temperature alone, right? So what you should verify is that clearly here, for instance, this should be 0. You can easily check that. So P times for the ideal gas, dP by dt is R over P plus P times dP by dV. What is dP by dV for the ideal gas? Minus RT by V square. You can easily verify that that is C. Similarly, you should be able to verify that dH by dV at constant temperature must also vanish from the ideal gas. I'm not able to locate that, but you should be able to easily verify from the general expression for dH by dV at constant temperature, where we have it. So anyway, it's there, is it? Yeah, here it is. E minus T dV by dt. dV by dt can also be easily, we don't even need question. Invertibility is universally it's there for the ideal gas. dV by dt is what? R by P, right? P minus RT by P is 0. So it's very easily verified. The H is, you just verify it. In the definition itself you can see H of the ideal gas must also be. But very important to recognize, the entropy of the ideal gas is a function of both volume and temperature, or pressure and temperature, whichever way you want to choose to do it. So that property of the ideal gas that depends only on temperature is restricted to E and H. So all the other three properties A, G and S, and you can easily see what that also, those are very important relations actually. I probably erased that, but you can see that let's now look at maybe list out the properties of the ideal gas. Because those are important properties, we later on need them. So ideal gas, E is the ideal gas. Okay, ideal gas is, this is basically assumed. The rest of it follows from these relations. This is something that we assume. So say that E of the ideal gas is a function only of temperature. H of the ideal gas is a function only of temperature. Cp minus Cv, the ideal gas, is R. Right? And what about S? For example, that's an important property, right? So if I take Sig of dT, I can ask what is Psig by dt. Psig by dt is Cpig by T. That is, there's no problem with that. Is equal to ds by dt. We know the general equation is dP by dt, right? So for the ideal gas, it would simply be R over V. R over V, sorry. dP by dt for the ideal gas simply R over V. This is a very important relation. It's important because it's independent of temperature. Sig is very much helpful in integration. When you're integrating something over volume and temperature, you will get that for the ideal gas it will split into two separate entities, one over volume and one over temperature. We later on see. Now again Sig of dP, Psig by dP. You see ds by dP is minus dV by dt from one of the Maxwell's relations, right? What is minus dV by dt? So d is RT by V. dV by dt is R over T, and so minus R over V. Of course, Psig by dt at constant pressure is simply Cp of the ideal gas divided by temperature. So this is again any Cp and Cv are related to the equation of state that is valid for any substance. This is generalization of this. You can ask by Cp and Cv is R for the ideal gas. What is it for a general substance? This is actually given by this somewhat complicated looking expression that simplifies considerably to the ideal gas. It's a constant actually. If I know Cv, then I pretty much know Cp for any substance. For any other substance to calculate the relation, we need the information about the equation of state, but not for the ideal gas. It's a universal constant. That means the same for all ideal gases. Are there any questions? So what I would like you to do is redo the same thing. I will hand out a list of all this formula so that you have them all in one place, right? But you should be able to derive them very easily. The only thing that is left is for A and G. What are the formula? We'll then see some importance of these coefficients. One of the main objectives of deriving all this is to be later on able to calculate the change in properties. Change in enthalpy, or change in entropy, or change in Gibbs free energy, because some of the most important quantities, right, change during a process which goes from one equilibrium state to another. Right? So to calculate the change, we need the derivatives first before we can integrate. So that is one objective. But some of these derivatives, some of these coefficients, we will see are directly useful in some practical applications, and we will see how those coefficients can be derived from these coefficients that we have, some other coefficients that we will introduce, so that you get to know that these are not just some finally they derive some mathematical expressions, but how we use them and what they mean and how they can be used profitably to get information about specific practical quantities of processes is what we would see from now on.